Anybody in the audience who's from the UK or either from the UK or in the kind of statistics Bayesian community, which is not everybody here, will of course know Professor Sir David Spiegelhalter will need no introduction. Star of television and radio. In addition to that,
we're looking him up here.
But the important point for those then the people who are not from the UK and who are not in the Bayesian statistical community, therefore might not know, and that includes I know some people from the legal community outside. They also should know that amongst his many achievements, one which has particularly affected the work I do is that David was one of the key people in effectively creating the revolutionary change in making basically Bayesian inference in Bayesian networks possible.
Right, okay, great, thanks very much. And amazing, you all stayed to the end of Friday afternoon, and I promise I will not go on for an hour. I don't know what people were doing sticking me on at this stage and giving me an hour. Oh, terrible. So I won't do that. And the other thing is that I'm going to talk largely outside the legal field. You've been doing all the details about what can be used in court and the difficulties of eyewitness evidence. I'm going to take a broader view and not get down to that detail. It's actually more of an ideas, the idea and the challenge of communicating these tricky numbers about evidence and how other fields are dealing with it and whether something can be learnt from them. So I'm going to start off with a recent case, in quotes. And the case on Saturday 25th, 2012, archaeologists started digging in a car park in Leicester, the site of Greyfriars Friary. It's actually it was in the car park space, marked R, I think. And they started digging in this car park and immediately found a skeleton, right where they started digging. The very first day they started digging, they found their first skeleton. There it was, curved back. So they said, oh, it's obviously Richard III. So, I find it deeply suspicious that they found him immediately. They dug up lots of other people afterwards, but that was the first one they found on the first night. They could have just stopped there, and that would have been it, one afternoon. So, we know about the likelihood ratio. That's the probability of the evidence if the skeleton is Richard III, probability of evidence if the skeleton is not Richard III. Now, I've just been talking to David Balding, who was involved in this and who could, but I won't ask him now, to describe there are actually two other, this could be broken down into two sub-hypotheses, the bottom one. But that's one we're going to take, because that's one that's published. Okay, so, blah, 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 we know about that. And here's a paper in Nature Communications, including Mark Thomas and David Balding, on the identification. And these are the main estimates of the likelihood ratios associated with the primary sources of evidence. The radiocarbon dating, fairly weak there, 1.8. Age and the sex of the skeleton, 5.3. Scoliosis is 212. Now this required an estimate of how many people in 1485 were wandering around like this. Now, this is not the sort of data that would be acceptable in R versus T. So we have to decide post-mortem wounds, because they found the wounds on his skeleton, and the fact that he'd been after he died, the body had been thrashed around and stabbed and everything like that. Mitochondrial DNA 478, the Y chromosome was evidence against, which was put down, I think quite reasonably, as gaps in the paternity line, since Richard III. I mean, he had no direct descendants himself, but from known, did not match the known descendants of male relations. So, but that's quite possible, can be explained by gaps in the paternity line. So, and so you multiply those up, you get 6.7 million. And of course, they didn't just do that. Pages of sensitivity analysis to these likelihood ratios. But I think it's a beautiful example of the use of combining evidence, assumed independent, idiot's Bayes, but still with a very powerful final likelihood ratio, and showing the balance of evidence and where the main contributions are coming in. But would this be accessible? Would these stand up in court? Would you be able to use these in court? But they were based on huge numbers of subjective assessment, historical assessments. Very few of those would stand the scrutiny of that's especially after R versus T, has been said that the acceptable statistical evidence, can only be used when essentially is based on large databases and largely restricted to DNA evidence. Generally not based on large databases. There are many assumptions, there are alternative possible values. Okay, so what can you say when you're not extremely confident about the likelihood ratio? And that's what I want to talk about. I want to talk about the fact that we can assess these likelihood ratios, how some are better than others. And not just in likelihood ratios, but in every area of stats where we're communicating, some numbers are better than others. Okay, now so we've got to try to separate, and this is quite tricky in our minds because evidence, the word evidence is being used in two different ways in this context. These are used as value of likelihood ratio is used as the measure of evidential strength, but we're also going to talk about the evidence for these likelihood ratios. So we're talking about evidence in two different ways, and it gets very confusing in this area. In other areas it's a bit simpler because we can talk about an estimate and then evidence for that estimate. In this case we're talking about evidence for these evidential weights. Okay, so let's actually assume for a moment that the likelihood ratio is known, is confidently known. Let's forget for a moment about our uncertainties about it, and we can look at various scales which we've seen this week, of which people have suggested. This was the AFSP suggestion, and then we've also heard from the ENTSI, the EU scale of this, on a log scale, very similar to the other scale, but with values of the likelihood ratio, 10 to 100, for example, providing moderate support, moderately strong, strong, very strong, extremely strong, and so on. And the other thing is that this one, and it's a quote from the ENTSI report, it very strongly says that it's quite reasonable that these can be formed by subjective probabilities. And the ENTSI report does not say these have to be based on substantial databases. Now, actually, I wonder, I think I've got some of these wrong, because there's a big gap here, 10,000 to a million and then a million above. So one of the things, yes, I've got this wrong. Oh dear, this should be about 21 there. What I've done, and something I'm going to be doing in some other examples, is to try to think of analogies, metaphors, correlates, to give a better feeling for what the size of these numbers means. And I'm going to show in other areas how people have done the same thing. They've taken a metric and then transferred it to a scale that might be more interpretable. So the one I'm going to use is this one that, I've got a coin, either it's fair or it's two-headed, one or the other. And I flip it and it comes up heads 3 times. So the likelihood ratio in favor of it being two-headed is 8, and that would count as weak evidence according to the ENTSI scale. If I do it 6 times and it comes up heads every time, 64, there's moderate evidence. 9 times in a row, so this coin is either two-headed or fair. You flip it heads 9 times in a row. Whoa, beginning to look fairly strong here. Moderately strong, that comes out according to the ENTSI one. And so on, and I didn't realize ENTSI goes from 10,000 to a million is that one, and this is above a million. So this would be 21 times. To get to extremely strong evidence, 2 times, you have to do it 20 times in a row. So 20 heads in a row as evidence between a two-headed coin and a fair coin would be extremely strong in the MTC thing. Now what this is just doing is trying to get a more intuitive calibration for the use of these words, because what I want to show is that in other areas the use of these words can lead to extremely misleading conclusions. So Rich III, when we convert to the ENTSI scale what the weights of evidence were, there's weak support, we support moderately strong, moderate support, moderately strong, and weak against. And those combine to get an extremely strong. So there's a metric in which these words are combining, which I don't know what you feel about it, we can talk about it afterwards. I don't think that's not unreasonable. But people can be given that information, because when you use verbal expressions for uncertainty, it can lead to all sorts of problems. So what I want to do now is look at other areas where people, good people, thoughtful people, have tried to do similar exercises. They try to take complex metrics and convert them to make them communicate so they can communicate them verbally to untrained people, essentially. So the classic one is climate change. They've spent ages, decades, trying to make consistent treatment of uncertainties in climate change. And what they've come up with in the end, not actually did some time ago, but they've finally managed to get their authors to use this in a consistent way, is this scale for probability. Very likely, well, Norman knows about this because he had to discuss it in the program we made together. Extremely likely is 95%. And I say extremely likely and above because that's what they conclude. That was what anthropogenic causes of at least half of the temperature rise in the last 100 years. Extremely likely.
Well, in the summary report, they made positive fallacy, of course.
Oh, yeah, well, yes, exactly. Well, we won't, let's not be picky. We've been told we shouldn't be picky about this sort of stuff. Anyway, so those words. Now, and so what happens is that in the report, they use those words and yet continually remind the reader of what those mean at the bottom of the pages. So that they use those words in the report. Now, there's been a lot of studies of people's understanding of those words. The biggest one recently was based on 25 samples, had thousands of people in 25 countries, I think 26 languages they were translated to and that sort of stuff. Because they're translated, not quite sure what happens in the translation, but basically it shows that each word, they were given what likely means, for example, and of course then you get a huge range on what likely means, from about 20% up to 80, 90%. And even if you give the VN, verbal numerical, you give them the scale, they still give very vague numbers for what likely means. So by giving them a word and a scale, you do get a better translation of the word into a number, but it's still not perfect at all. People just don't seem to seem to be able to want to choose numbers that they feel are what they understand by likely. The crucial thing from all this research, there's been so much research, is that words like this have no consistent meaning outside a context. They mean different things in different contexts. And one of the classic examples is on your drug. If you are taking any medicines, if you look at anyone in the EU, if you've got any tablets with you, even paracetamol or anything like that, you take out the patient information leaflet, great long white piece of paper like that, and it'll give you about 8 pages in small print of all the possible side effects that you might have. And so, for example, if you've got a statin, I don't want to know, but if you look in your statins, and it'll tell you that constipation is a common side effect. So if 100 people take statins, how many would you expect to get constipation? Cool. Well, what would people interpret that as? What would common? What would you say? Would you say?
5 and 100.
Sorry?
1 out of 100.
How many?
1.
70. 70. Common. What's common mean to you?
But it's a side effect, so we already know it's rare.
No, but exactly. So what David said is the side effects you already know it's rare, because common in the whole world of side effects has got a completely different meaning from common in everyday usage. And so let's do pancreatitis, considered a rare side effect. 100 people taking statin, how many will get pancreatitis? Yeah, very small. Okay, so the risk, constipation is actually 2.5%. So that's the figure, the actual figure, and that's considered as common. Pancreatitis is 0.04%. What's that, 4 in 10,000, 1 in 2,500? That's considered rare. And the reason these words are used is because they're mandated by the EU. No, not for much longer. No, I didn't vote. I voted Remain. It's all right. Don't blame me. What?
There's also the issue of, is it a common side effect amongst all side effects?
Well, the point is, though, that those words, you can think about what those words mean, but those words are just given, and people will interpret in a different way. And people have done research, and the average for constipation is about 34%. People would say that's what they would expect it. 34% of people with statins would get constipation. So these numbers these words don't represent the usage. They represent usage among people who work in adverse drug reactions, but nobody else. And that's those are the regulations. Those are the words that must be used. So it's very similar to the likelihood ratio scale, but they've chosen and the suggestions, similar kind of attempt on a log scale, but ones that don't bear any resemblance to popular usage.
And I'm sorry, it just seems to me obvious that what's meant is among all the people in the whole country taking statins, thousands of them are having constipation, and it's understood that that's what common means.
Oh, you see, common, the meaning that lots of people.
Yeah,
but this common would be used for a drug that only a few people are taking.
Yeah.
The same word is used, even if only 10 people in the country are taking the medicine, it'll still be common.
When?
Well, no, that's the officials. Now, you might, just because statins are common, maybe with statins, maybe that's a bad example, because people might think that's what common means. But, yeah, common lots of people. But actually, what it should reflect is the chance of me getting it. That's the important thing, not how many people in the country. I don't care how many people are constipated. I want to know if I'm going to get constipated. Come on. And you're allowed to say frequency not known. Remember that. Okay. So, all right. So that's my statement about the use of verbal scales. I like it, but it's got to be used extremely carefully and needs to be empirically researched. That's people have been trying to do. You know, I'm not saying people haven't done that with likelihood ratios. And I'll come back to the analogy thing later. Now, how do we get, coming back to Richard III, something I mentioned, how do we get the fact that to separate that the assessed probability effect size likelihood ratio thing, some are better than others. With Richard III, some were better than others. These numbers, just saying likelihood ratio is 47, think, well, you know, how good is that 47? And so you were trying to separate that from the underlying quantity quality of the evidence underlying the assessment, essentially our confidence in the assessment. How can we do that? Okay, well, some of the options are, first of all, don't do things to 3 decimal places. You know, the vagueness in the number can be quite well assessed quite often just by using very round numbers. People don't interpret those things. You can give an actual interval, but the point is that any interval based on statistical analysis will be a gross underestimate of the uncertainty, because it'll only take into account sampling variability, and we're talking mainly here about systematic biases. It's the most crucial thing, lack of good quality evidence. We could do, as they did in Richard III, lots of sensitivity analysis, lots of values, and try lots of things and show, well, it could be between here and here, and it wouldn't make much difference if it were, and so on. Very nice thing to do. We could only specify up to a band, which again is what's being done for the side effects and for many areas. So all these things are just giving a vagueness, a feeling about it. We could use verbal qualifiers as to the confidence we have in the numbers. For example, in patient information leaflets, the breast cancer screening one gives some numbers and it says these are the best expert current judgments. So it sort of gives a lot of qualifiers on the quality of the numbers and not to be taken too seriously. Or we could just refuse to give a value. If things are bad enough, we could refuse to give a value. So these are all options that people use to express some degree of vagueness about these numbers. Now, this is the thing I'm really interested in, are alternative vivid metrics for effect sizes. Now, and there's some lovely ones that people are doing. Okay, the Education Endowment Foundation is the body in the UK that's in charge of synthesizing and communicating the effects of different school interventions. Arts participation, aspiration interventions, and things like that. And for every one of these, they give it a rating system. It's like TripAdvisor. They give a cost rating at the start. They give this, which is the evidence strength. And in terms of the effect, they do months of impact. So their metric, their effect size metric, is how many months advance in the education. This will give you 2 months, advance your education by 2 months. So isn't that a clever metric to use, rather than some subtle effect size measure on some educational scale and things like that? So block scheduling, collaborative learning, get 5, it's cheap, good evidence, 5 months, yes, let's do it. And some of them are terrible. The worst ones is staying down a year. I should have put that up. Keeping people down a year is the worst one of all. It's just dreadful. But others, block scheduling, it's cheap, not much evidence, and it's no good, etc., etc. But that's, behavior interventions, pretty good there, but it costs a lot. So that's what they're doing. They're doing this with all these interventions, putting this evidence together. Very powerful, I think. And then they define what an evidence scale. Limited, moderate, extensive, very extensive. So this is the confidence, the evidential strength behind their assessment of the impact. A metric that I've been developing, and not just me but others, is the idea of effective age. I just had a paper published on this. So instead of communicating, here's a whole lot of behaviors that you might have. Watching 2 hours of television a day, being 5 units of BMI heavier, having some exercise, eating fruit and vegetables, smoking 20 cigarettes, taking statins, instead of communicating those in terms of hazard ratios, which are incomprehensible to everybody and give a misleading relative risk measures given a misleading impression, you can convert it to how much older or younger it makes you in terms of your annual risk of death. So 20 cigarettes a day, 8 years older. It puts 8 years on your age. Shut up. So just a minute, Ted. 2 years, I'll answer you in a moment. 2 processed meat, bacon sandwich a day, 2 years older, if you eat a bacon sandwich a day. And 2 portions of vegetables a day, a year younger. You take a year off your age if you eat your 2 portions of veg a day. Yes, Ted.
So is that +8 the same for a 70-year-old as for a 20-year-old?
Yes, and the reason why, and this is what's so cool, is that every year between 9 and 90, apart from a bulge when you're young, your risk of death goes up by 9%. Hazard ratio is roughly log linear. The hazard is your underlying hazard ratio. Everybody, your annual risk of death goes up by 9% per year. So being a year older is associated with a hazard ratio of 1.09, no matter how old you currently are. So all you do is do these, what power of 1.09 these are, and it'll tell you how many years older or younger it makes you. That is, and in the paper I got a little theorem showing under what conditions is this independent of age. So I think this is very powerful, and it's being used, the idea of your heart age, your lung age, eye age, brain age are being used extensively now to communicate the impact of behaviours without having to use a metric. So there's another idea of a metric, and I suppose it's like the coin flips for the likelihood ratios. Are there metrics that could be used that had a much more vivid feeling for what these numbers meant? Crime. What works in crime reduction? Again, on a website in the UK, you can find alley. I don't know what alley. Oh, alley. Yeah, putting gates on alleys. That's amazing, isn't it? Who would have thought it? Anyway, alcohol tax and price policy. You get the impact. That's the effect. So that's the effect size. How it works. Your knowledge about the mechanism, where it works, how to do it, and what it costs. On a star rating there. So this is about. So I think it's great. People in the UK are working through policy after policy area after policy area, communicating this way, and always you've got a measure of its estimated impact and the confidence you have in that analysis, and that tells you what the effect scale is. They haven't got a nice metric like months, older or younger that it makes you. They haven't got that, and this is the effect. This is how good the evidence is, to do with how good the systematic review was, etc., etc. So, and the same people have done in climate change. These probabilities are given, but if the evidence isn't good enough, they won't give those probabilities, essentially. So they've got not only a probability scale, but a confidence scale, showing how confident they are in the science underlying the probabilities. So if there's good evidence and good agreement, there's high agreement, then they get a high confidence. And what they say is you should only give numbers for reasonably high confidence. Below that, at this level, you might just be able to give a rough range or a rough magnitude, order of magnitude. Can't give a precise number. So, for example, you won't be able to read, the anthropogenic influence is likely, that's more than 66%, contributed to the retreat of glaciers, blah, blah, blah. But when it comes to Antarctica, due to a low level of scientific understanding, there is low confidence in attributing the causes of the observed loss of mass from the Antarctic ice sheet. So they're saying, we don't know whether man has caused the loss of the Antarctic ice sheet, and we're not going to give a probability to it.
That's easy to misinterpret, though, isn't it?
Well, yeah, what do you...
When it was low confidence, I would almost have interpreted it as mean that there wasn't, rather than there. No confidence that there was.
Saying they thought that it hadn't actually gone down. Oh, their confidence gone down, they're low confident in the attribution.
Yeah, but I think people might find out.
I'm not going to start saying about the text of the IPCC reports, which is something we do not want to go into. But they are doing. I feel they're doing their best. They're doing their best. Cochrane, and of course, in medicine, people are doing exactly the same thing. This is an interactive summary of findings tables with the effect of a drug versus warfarin for atrial fibrillation. You get an estimate of the effect in absolute numbers and relative effect, and then a certainty of the evidence, the grade scale. Again, there's 2 levels. What the estimate is, And this is more than just a confidence interval. This actually says how strong the evidence is underlying the estimate. You get confidence intervals as well, but those are both based on statistical analysis. So the grade scale is very widely used. Again, a four-star system. Interesting that in intelligence estimates, been a long argument, particularly in the US, people trying to get people to use numbers in terms of intelligence estimates, and which has come and gone for decades. For this recent, words of estimative probability of the if you Google that, you can find a fascinating history. So, but now they seem to have retracted largely and said we don't have to, it's really seemed to have gone backwards on this. Not using numbers, we say probably, likely, almost certainly. So it's similarly, we use words such as we cannot dismiss, we cannot rule out, we cannot discount. I mean, it just seems to have gone back to the sort of things that you've been criticising all week, the use of these very woolly words being used. But that's clearly not always the case. When they were planning on the Bin Laden attempt, people were giving probabilities there that he was there in the compound. They had a red team, CIA red team, specifically trying to find all the problems there would be. So Mr. President, if we had a human source who told us directly that Bin Laden was living in that compound, I still would only be at 60%. And Obama said, in this situation, what you started getting was probabilities that disguised uncertainty, as opposed to actually providing you with more useful information. So in that sense, people giving him lots of probabilities. It's been argued since that some of the intelligence community should have ganged together and produced a single composite probability that was then given to the president, rather than him getting lots of different opinions, which I disagree with, but I don't think that's appropriate. So again, it shows that I still think, personally, probabilities are a good thing. Because if you the intelligence community also then recommend we can use these words like probably, likely, and then we can also say how confident we are in our assessment. So again, they're putting the second level in, like IPCC, and the confidence means the information is, if it's low confidence, it's scant, questionable, or very fragmented. So you can see what they're trying to do. I think it'd be much better if they had numbers at the top level.
What do you mean by degree of likelihood there?
Sorry?
Degree of likelihood in the first.
Oh, that's this thing. It's this. But it's not. They're not giving numbers. They're just saying they're allowing them a few words, like probably, likely. But they're also allowing them to say maybe and suggest and things like that. So it's very vague at the top level now.
Well, since you are using likelihood to say probability, just to be.
Well, they don't. Well, some. Again, this argument is probably still going on in the CIA. I haven't got a clue, but apparently people have been arguing for decades that some people want to put numbers on, and others argue against it. Okay, so just to sort of conclude, I came up with it. In my mind, I sort of think, well, couldn't we do this with all sources of evidence? Couldn't we give, just like they're doing in education and in crime and in health, couldn't we give our evidence a simple star rating? Couldn't we just do that in general? Which we could redefine according to the context, but couldn't we do that? So I invented one, because I got a chance. It was the Government Chief Scientific Advisor's report, and I just said, the quality of a risk analysis. And basically what I want to say is some risk analyses I really believe, they're based on fantastic evidence, they're really like a roulette, where I feel confident about that it's not biased. That's a 4-star risk analysis, down to 1 star. So what I'm saying is that 4-star, for example, this is where you can understand the underlying process with reasonably good numerical risk. Playing roulette. That's a 4-star risk assessment. You can't say what's going to happen, but you know what the probabilities are. 3-star, reasonably confident. We can expect some numbers to change a little more, but not sufficient to justify major policy shifts. So statin risk. We're not going to discover anything major about statins now. There's so many people have taken them. Nothing's big. We're pretty confident. We're not exactly sure about what the side effects are, but we're pretty confident. That's a sort of 3-star situation. And then you get a bit more ropey. New evidence could have a substantial impact on our assessment. So we need to be robust. We need to be some precaution adaptivity. Zika's an interesting one. I was on the committee drawing up the guidelines for British people visiting the Olympics. And you could just see over the months the Zika thing going essentially from 1 star, where people really haven't got a clue, up to 2 stars. And some bits of it reasonably getting to 3-star now, to some extent. But it's just crawling up there, where you're really not quite sure what the numbers are. And that we ended up getting the experts to give give numbers for the risks. They didn't really like it at first, but they did in the end. But ranges, couldn't get them to a single number. 1 star, well, I haven't got a clue really. You know, your guess is as good as mine, almost. And we've got to look for resilience to unexpected things. This is where the unknown unknowns come in. We can't even map out the possibilities. Really, watch out, be cautious, be very careful indeed. So, to conclude, any likelihood ratio is always based on assumptions and judgments. We've heard that as well. It's never correct. But some are better than others. Yeah, some are better than others. Now, how could we communicate that some are better than others? Can we give them star ratings? You know, can we actually say this is a 4-star likelihood ratio and define it? And so, but also maybe we could just communicate them as, you know, likelihood ratios where we can actually put a number on it. We're so confident about it, we're willing to put a number on it. Maybe, you know, again, ENTSI, for example, in their book, their guidelines provide some case studies where they say about 400. You know, they give a rough number. Maybe we just put a band with a verbal descriptor of the kind we've seen today. And maybe we just say we don't know. You know, maybe that's a reasonable sort of star rating on a 3-point scale. Maybe we could do better than that. But I really think it's worth exploring. The public understanding of the language of uncertainty is an empirically researchable issue. And people are doing this in many areas indeed. And the legal world is strange. It's got its bizarre rituals, and for me, you know, very odd habits. But never mind, other areas have as well. And each area is trying to tackle that problem. Education, I mean, crime, really difficult to get evidence, you know, included in the policy decisions. But they're all trying, and actually they're all trying to do very, very similar things. So I think it's worthwhile learning what other people are doing. Okay, thanks very much.
I can't resist a quick anecdote. One of my favourite numerical matches of verbal to numerical evidence was in doctors getting women to be screened for Down syndrome, where they would say, you're at very high risk of having a Down syndrome child. It's 1 in 200. And then if the woman asked about the risks of amniocentesis, oh, there's a very, very low risk of miscarriage. It's only 1 in 200.
Yeah, that's still on NHS choices.
It's still on their choices.
NHS choices. The 1 in 100 risk of miscarriage is defined as being a lower risk than the 1 in 250 for the amniocentesis. It's still there.
I really like your perspective and what you present and the ideas, but I'm having trouble getting my mind around something like someone saying, we have low confidence that there's a 90% probability that a hurricane will hit Miami.
Yeah.
Are you talking about anything more than wide dispersion around a point estimate?
Yeah. Well, I mean, that's the problem. That you're into second order statements about it, and a lot of the time you don't want to do it. You know, you wouldn't want to do it. If you want to just give a message to the public, just like you just give an estimate, and we think there's this chance. But of course, in some areas, you'll be much more confident about the hurricane hitting Miami than not. And not confident it will hit them, but confident in your probability assessment. You know, you're much more confident in some weather models than other. You know, you might be much more confident in your probability of rain than you are in your probability of the hurricane hitting it. So for some audiences, that expression, that second order stuff is very valuable. But you have to choose whether you want to use it or not, because it's been shown again in risk communication to individual patients that for some, if you tell them, you know, you've got a 30% chance for heart attack, stroke, but actually we're not very sure about that, or for people like you, we've only got limited data, so we're not very sure. For some people that's actually reassuring, and others you just think, well, no, I'm not going to trust anything you say at all. So that has to be done with great caution to acknowledge this second level of the confidence in the main number that you're giving in your communication. You shouldn't just bash it out routinely, because it can make you look completely hopeless.
So it's a slightly related thing. If we're talking about confidence in likelihood ratios, people might think something like about, like variability or something or other like that. But there's a sort of separate issue, and this our Richard III calculation sort of epitomizes this, that there was a very clear notion of being conservative, so that
I should have said
we
those
made all
conservative
these
values,
judgments about where there were multiple sources of information. We chose the most conservative one, so we're not confident in those likelihood ratios in the sense of being correct in any sense, which, as you say, is not really very meaningful. But we're confident that no reasonable person would choose a lower value.
And I should say, I actually should have pointed out that one approach to doing this is to deliberately pick one end of one end of the range of the possibilities, which is what you did there.
And so, with conservative judgments, you can be confident even in the presence of little information.
Exactly. I must remember to add that in.
So one of the problems we see with the interpretation of likelihood ratios in the forensic context is that lay people often misunderstand what it is that the expert's telling them. I mean, the expert's telling them something about the relative likelihood of some observations under certain hypotheses, and they misinterpret it as a statement about the probability that these hypotheses are true. And that can create problems because it discourages them from paying attention to other evidence that also relates to the hypotheses and so on. And lead to problems. And so I guess one question I have is, can you think of ways to deal with that problem? I mean, one of the suggestions that's been made is that people may be better at dealing with natural frequencies than likelihood ratios, so somebody could convert a likelihood ratio to some natural frequency equivalent and say, here's a likelihood ratio of 1,000. That would be like finding a characteristic that would occur in one person in 1,000 shared by these two items.
Now, first of all, I completely agree, and that's why I actually like the table that are put up for Richard III, because that makes clear that apart from the 6.7 million possibly, each of those numbers is a contribution, and you wouldn't take each of those numbers and turn it into a probability that it was Richard III. So it's quite clear that these are contributory factors. And the other thing is that while in terms of I would convert any probability to an expected frequency out of 1,000 people expect that. It's extremely difficult, dangerous to do that really with likelihood ratios, because it even more gives the feeling, I think, of turning them into probabilities. And that's what you want to avoid doing. And that's why I put the coin analogy up, which is kind of what I feel is almost an attempt at a natural frequency interpretation of likelihood ratios. Trying to reduce things to whole number visualizable experiments with equivalent strength of evidence.
Yeah, but what about there's still this danger of inverting the conditional probability. Any suggestions on that?
Obviously hugely careful use of language, and again the idea that never to think that this is the last word. So it's not the probability, you're never talking about the probability, you're only talking about how this adds to the available evidence. Maybe something, always making that clear.
I wanted to ask about the star ratings. So based on the observations, do people tend more to trust the results if there is a low star rating or if there is actually a number given to it?
I think that's really, I don't know if people have explored that, whether if you tell, but that's exactly right. What would be more trustable? You could explore that with the education one, because sometimes you've got some big effects with very poor evidence for them. So there's been some crummy studies that have found some big effects, and the other ones would be moderate studies where there's a lot of evidence. I know some evidence for this. We've done some psychological studies where people were asked to compare hospitals. One hospital had done 100 operations and got 99% survival rate. Another operation had done 1,000 operations and got 97% survival rate. Which hospital would you rather go to? And the majority of people wanted to go to the bigger hospital. So they were taking notice of both, but they were actually, the confidence was overwhelming the point estimate. So, which is also, you could think of that as sort of Bayesian shrinkage, but majority of people, I think, did the right thing. I would do that, and they were doing the right thing. So that is some empirical evidence that people can juggle these ideas in their heads, and that might prefer a confident figure that didn't look quite as good. Because I think people have got this feeling of too good to be true. Oh, there's only a little. People are not stupid, I think. Yeah.
And is this increases with when you're asked to kind of force the opinion in some scale? So for instance, if you have a scale like, are you unlikely to go, you probably would go, or you're very likely to go. If you have 3 categories of 5, would it make a difference or not?
Well, the problem is, though, you know, any of these, there's been endless experiments showing these words mean almost anything to everybody, and they crucially dependent on context, the individuals, enormous variability. And you know, you could say that all these attempts that people are making us to standardize these words, not saying this is what likely always means, but in this context, this is what we mean by likely. So I think that, you know, I like the use of words, but it's got to be done very, very carefully.
Yeah, but still a comment about representing the evidence in form of this ratio. Okay, and I like your example, which I always do in my teaching about the die, which the die is nothing but log 2 of the
ratio, log 2, yes,
of the
exactly.
base factor. I think there was historical attempt to introduce the log 10, like the pairs, the weight of evidence, weight of belief. And now that, for example, it's fashionable, especially in UK, Alan Turing, okay, he was called the ban, exactly, and the deciban, which I think if you train some people, I think it is a nice name because it is related to Alan Turing, very important during the war, and 1 deciban, it is, 4 deciban is 1 die for you, and it has the advantage that you can go positive and negative.
I
don't know.
I know it's nice, but I mean, it'd be okay if you had a 10-sided, a well-known 10-sided randomizing device, which of course there is just picking a random integer, then it's much more natural to use that. But actually, people are used to coins and dice a bit more, I think. That's the trouble.
Negative.
Yeah, exactly.
Okay, so unless there aren't any other burning questions, the last question of the workshop is going to be good.
Well, actually, I just wondering whether there's a few other things to unpack in terms of when you mentioned how resilient your conclusion is to new evidence. And that may be slightly different from how good the evidence is, because you're understanding the system and maybe the stability of the system to make that.
You know, you did know. I slid that in quite subtly because I really like this idea of the fact that your confidence is very strongly related to how much you might change your opinion in the future. And that's been shown with intelligence analysts. The time they're least happy about giving a number is when they feel there's some important bit of information that they could know, and they might know soon, but they don't know yet. Which would change their mind dramatically. And that's very unsettling. That's very psychologically unsettling indeed. And grade, for example, their first definition of their scale was in terms of further research evidence might change your opinion. And I really like that. Then they changed it to just, our estimate is rather uncertain or something like that. And I thought, oh no, you wrecked it. So I'm sticking to their old one.
That feels like a really good saying that people can understand.
Well, it's very operational. It gives a much more feeling of what uncertainty means. It means that your opinion might change dramatically in the future on receipt of further evidence. And I think that's a very powerful image that people can understand.
It's also potentially very helpful to politicians because, of course, when people say, why on earth did you do that, you were so stupid, they can, they said, this was the evidence at the point at which a decision had to be made. And if people are used to that expression of uncertainty, it could change because we need more evidence. There's less scope for the naive blame game.
But you're right, in fact, that it does make it context, because in some contexts maybe it's completely impossible we'll ever get any more evidence, and that's it. We've reached the end of our explanation. We just have to give an assessment. So you're right that it wouldn't work well in that context.
Thank you very much, David. Fantastic talk and very good question and answer session.
Thank you.